Learning objectives. At the end of this topic, you will be able to explain the process of refraction of light, explain and demonstrate the phenomenon of refraction of light through a rectangular glass slab, explain the meaning of the terms refractive index and optical density and their correlation with the speed of light, understand the process of refraction by spherical lenses, explain the formation of images through lenses, understand the meaning of magnification and power of a lens. Introduction. Rita and her mother. Light seems to travel along straight-line paths in a transparent medium. What happens when light enters from one transparent medium to another?
It appears to be a more brighter light.
Right. You might have observed that the bottom of a tank or a pond containing water appears to be raised. Similarly, when a thick glass slab is placed over some printed matter, the letters appear raised when viewed through the glass slab. Why does it happen? Have you seen a pencil partly immersed in water in a glass tumbler?
Yes, it appears to be displaced at the interface of air and water. This is also true for a lemon kept in water in a glass tumbler, appearing to be bigger than its actual size when viewed from the sides.
We can also observe that a pencil appears to be displaced to the same extent if instead of water we use liquids like kerosene or turpentine. We will find that the extent of the effect is different for different pair of media. These observations indicate that light does not travel in the same direction in all media. It appears that when traveling obliquely from one medium to another, the direction of propagation of light in the second medium changes. This phenomenon is known as a refraction of light. Let me tell you more about this phenomenon in this chapter. Refraction of light. Refraction through a rectangular glass slab. To understand the phenomenon of refraction of light through a glass slab, let us do an activity. Fix a sheet of white paper on a drawing board using drawing pins. Place a rectangular glass slab over the sheet in the middle. Then draw the outline of the slab with a pencil. Let us name the outline as A, B, C, D. Fix two pins, say E and F vertically such that the line joining the pins is inclined to the edge AB. Look for the images of the pins E and F through the opposite edge. Fix two other pins, say G and H, such that these pins and the images of E and F lie on a straight line. Join the positions of tip of the pins E and F and produce the line up to AB. Let EF meet AB at O. Similarly, join the positions of tip of the pins G and H and produce it up to the edge CD. Let HG meet CD at O'. Join O and O'. Also produce EF up to P. In this activity, we will note that the light ray has changed its direction at points O and O'. Note that both the points O and O' lie on surfaces separating two transparent media. Draw a perpendicular N' to AB at O and another perpendicular M' to CD at O'. The light ray at point O has entered from a rarer medium to a denser medium, that is, from air to glass. Note that the light ray has bent towards the normal. At O', the light ray has entered from glass to air, that is, from a denser medium to a rarer medium. The light here has bent away from the normal. EO is the incident ray, OO' is the refracted ray, and O'H is the emergent ray. You may observe that the emergent ray is parallel to the direction of the incident ray. This happens due to the extent of bending of the ray of light at the opposite parallel faces, AB, air-glass interface, and CD, glass-air interface of the rectangular glass slab, is equal and opposite. This is why the ray emerges parallel to the incident ray. However, the light ray is shifted sidewards slightly. Experiments show that the refraction of light occurs according to certain laws. The following are the laws of refraction of light. 1. the incident ray, the refracted ray, and the normal to the interface of two transparent media at the point of incidence all lie in the same plane. 2. The ratio of sine of angle of incidence to the sine of angle of refraction is a constant for the light of a given color and for the given pair of media. This law is also known as Snell's law of refraction. The refractive index. The refractive index can be linked to an important physical quantity, the relative speed of propagation of light in different media. It turns out that light propagates with different speeds in different media. Light travels the fastest in vacuum with the highest speed of 3 × 108 meters per second. In air, the speed of light is only marginally less compared to that in vacuum. It reduces considerably in glass or water. Consider a ray of light traveling from medium 1 into medium 2. Let V1 be the speed of light in medium 1 and V2 be the speed of light in medium 2. The refractive index of medium 2 with respect to medium 1 is given by the ratio of the speed of light in medium 1 and the speed of light in medium 2. This is usually represented by the symbol N21. This can be expressed in an equation form as N21 is equal to speed of light in medium 1 divided by speed of light in medium 2 is equal to V1 divided by V2. Similarly, the refractive index of medium 1 with respect to medium 2 is represented as N12. It is given by N12 is equal to speed of light in medium 2 divided by speed of light in medium 1 is equal to V2 divided by V1. If medium 1 is vacuum or air, then the refractive index of medium 2 is considered with respect to vacuum. This is called the absolute refractive index of the medium. It's simply represented as N2. If c is the speed of light in air and v is the speed of light in the medium, then the refractive index of the medium Nm is given by Nm is equal to speed of light in air divided by speed of light in the medium is equal to c divided by v. The absolute refractive index of a medium is simply called its refractive index. The refractive index of several media is given in the table. Refraction by spherical lenses. A transparent material bound by two surfaces, of which one or both surfaces are spherical, forms a lens. This means that a lens is bound by at least one spherical surface. In such lenses, the other surface would be plane. A lens may have two spherical surfaces bulging outwards. Such a lens is called a double convex lens. It's simply called a convex lens. It's thicker at the middle as compared to the edges. Convex lens converges light rays as shown. Hence, convex lenses are called converging lenses. Several rays of light parallel to the principal axis are falling on a convex lens. These rays, after refraction from the lens, are converging to a point on the principal axis. This point on the principal axis is called the principal focus of the lens. Similarly, a double concave lens is bounded by two spherical surfaces, curved inwards. It is thicker at the edges than at the middle. Such lenses diverge light rays and are called diverging lenses. A double concave lens is simply called a concave lens. Several rays of light parallel to the principal axis are falling on a concave lens. These rays, after refraction from the lens, appear to diverge from a point on the principal axis. This point on the principal axis is called the principal focus of the concave lens. A lens, either a convex lens or a concave lens, has two spherical surfaces. Each of these surfaces forms a part of a sphere. The centers of these spheres are called center of curvature of the lens. Image formation by lenses. Lenses form images by refracting light. Let's understand this with the help of an activity. Take a convex lens and find its approximate focal length. Draw 5 parallel straight lines on a table such that the distance between the successive lines is equal to the focal length of the lens. Place the lens on a lens stand on the central line such that the optical center of the lens lies just over the line. The two lines on either side of the lens correspond to F and 2F of the lens respectively. Mark them with appropriate letters such as 2F1, F1, F2, and 2F2 respectively. Place a burning candle far beyond 2F1 to the left. Obtain a clear, sharp image on a screen on the opposite side of the lens. Note down the nature, position, and relative size of the image. Repeat this activity by placing object just behind 2F1, between F1 and 2F1, at F1, between F1 and O. Note down and tabulate your observations. The nature, position, and relative size of the image formed by convex lens for various positions of the object is summarized in the table. Let us now do an activity to study the nature, position, and relative size of the image formed by a concave lens. Take a concave lens and place a burning candle on one side of the lens. Look through the lens from the other side and observe the image. Try to get the image on a screen, if possible. If not, observe the image directly through the lens. Move the candle away from the lens. Note the change in the size of the image. What happens to the size of the image when the candle is placed too far away from the lens? The nature, position, and relative size of the image formed by a concave lens for various positions of the object can be summarized in the table. Based on the activity, we can observe that a concave lens gives a virtual, erect, and diminished image irrespective of the position of the object. Image formation in lenses using ray diagrams. Ray diagrams will help us to study the nature, position, and relative size of the image formed by lenses. For drawing ray diagrams in lenses, alike of spherical mirrors, we consider any two of the following rays. 1. A ray of light from the object parallel to the principal axis after refraction from a convex lens passes through the principal focus on the other side of the lens. In case of a concave lens, the ray appears to diverge from the principal focus located on the same side of the lens. 2. A ray of light passing through a principal focus after refraction from a convex lens will emerge parallel to the principal axis. 3. A ray of light passing through the optical center of a lens will emerge without any deviation. The ray diagrams for the image formation in a convex lens for a few positions of the object are shown. The ray diagrams representing the image formation in a concave lens for various positions of the object are shown. Sign convention for spherical lenses. For lenses, we follow sign conventions similar to the one used for spherical mirrors. We apply the rules for signs of distances, except that all measurements are taken from the optical center of the lens. According to the convention, the focal length of a convex lens is positive and that of a concave lens is negative. We must take care to apply appropriate signs for the values of U, V, F, object height h, and image height h'. Lens formula and magnification. As we have a formula for spherical mirrors, we also have a formula for spherical lenses. This formula gives the relationship between object distance u, image distance v, and focal length f. The lens formula is expressed as 1 by v minus 1 by u is equal to 1 by f. The magnification produced by a lens, similar to that for spherical mirrors, is defined as the ratio of the height of the image and the height of the object. It's represented by the letter m. If h is the height of the object and h dash is the height of the image given by a lens, then the magnification produced by the lens is given by m is equal to height of the image by height of the object, which is equal to h dash by h. Magnification produced by a lens is also related to the object distance u and image distance v. This relationship is given by magnification m is equal to h dash by h is equal to v by u. Lens formula and magnification numericals. Let's solve a numerical. A concave lens has a focal length of 20 centimeters. At what distance should the object from the lens be placed so that it forms an image of 15 centimeters from the lens? Also, find the magnification produced by the lens. Solution. A concave lens always forms a virtual erect image on the same side of the object. Given data is image distance v is equal to minus 15 centimeters. Focal length f is equal to minus 20 centimeter. We need to find the object distance u and magnification. By using formula 1 by v minus 1 by u is equal to 1 by f, we get value of u is equal to minus 60 centimeter. Thus, object distance is 60 centimeters. We know that magnification m is equal to v by u. We get m is equal to minus 15 by minus 60 is equal to 1 by 4 is equal to plus 0.25. The positive sign shows that the image is erect and virtual. The image is 1/4 of the size of the object. Power of a lens. We've already learned that the ability of a lens to converge or diverge light rays depends on its focal length. For example, a convex lens of short focal length bends the light rays through large angles by focusing them closer to the optical center. Similarly, concave lens of very short focal length causes high divergence from the one with longer focal length. The degree of convergence or divergence of light rays achieved by a lens is expressed in terms of its power. The power of a lens is defined as the reciprocal of its focal length. It's represented by the letter P, capital. The power P of a lens of focal length f is given by P is equal to 1 by f. The SI unit of power of a lens is diopter. It is denoted by the letter D, capital. If f is expressed in meters, then power is expressed in diopters. Thus, 1 diopter is the power of a lens whose focal length is 1 meter. 1 d is equal to 1 meter to the power minus 1. You may note that the power of a convex lens is positive and that of a concave lens is negative. Opticians prescribe corrective lenses indicating their powers. Let us say that the lens prescribed has power equal to plus 2.0 d. This means the lens prescribed is convex. The focal length of the lens is plus 0.50 meter. Similarly, a lens of power minus 2.5 d has a focal length of minus 0.40 meter. The lens is concave. Summary. Let's summarize the topic. The refractive index can be linked to the relative speed of propagation of light in different media. Lens is a transparent material bound by two surfaces, of which one or both surfaces are spherical. A double concave lens is bounded by two spherical surfaces, curved inwards and diverge light rays. Ray diagrams will help us to study the nature, position, and relative size of the image formed by lenses.